All right, guys, so make sure you have your notes out. We're going to fill out the rest of our notes on our Unit 2, Matter and Energy, and we're going to focus on energy for this set of notes. So, energy is simply a quantity used to show the amount of work done. And we can have many different forms of energy, and we're going to be focusing later on thermal energy and chemical energy. But for now on, we're going to talk about some general definitions just to give you guys a starting point. Now, there are different forms of energy. We have kinetic energy, which is the energy of motion, and then potential energy, which is stored energy. Kinetic energy is when you see something moving, it has kinetic energy. When we talk about atoms and molecules in chemistry, we talk about the kinetic energy of the actual individual atoms moving. So remember, a solid has the least amount of kinetic energy. Liquid would have a little bit more, and then a gas would have the most amount of kinetic energy because it has the most movement. All right. The equation for kinetic energy is 1/2 mass times velocity squared. So M stands for mass and V stands for velocity, which is just another word for speed. There are different forms of energy. Main part, you might have heard of this before, is kinetic energy, which is the energy of motion. Okay, so we're talking about the energy of moving. When you're driving in a car, kinetic energy, you're moving along, rolling a ball, all those things. And when we talk about kinetic energy in chemistry, we're talking about the movement of the particles. So remember, particles are never not moving. Remember, they're always in motion. So we can talk about the kinetic energy that those atoms and molecules and particles have. Remember, a solid is going to have the least amount of kinetic energy because it has the least amount of movement. Liquid, a little bit more kinetic energy, and then a gas has the most kinetic energy. The equation for kinetic energy is 1/2 mass times velocity squared. So M stands for mass, V stands for velocity. Potential energy is stored energy. All right, so we're talking about energy. It's not it's available for use, and it's available to be transferred to another type of energy. So we can think about potential energy as a stretched rubber band, a roller coaster at the top of a hill, and a battery, all different types of potential energy. Potential energy then is our stored energy, and we can have energy stored in various ways. We can talk about a stretched rubber band has elastic energy. A roller coaster at the top of a hill has gravitational, positional energy. We have a battery, which has stored chemical energy. So we can have all different ways to store energy. So we can use energy. We can transform energy into different types. Okay, so different types of energy that we might transform energy to is mechanical energy, thermal energy, and chemical energy. Mechanical energy is talking about motion or position. Thermal energy is the movement of heat. So we're talking about heat always flows from warm to cool. And then chemical energy is the breaking and reforming of chemical bonds. Energy can be transformed from one type of energy to another. So we can talk about our different types of energy, including mechanical, thermal, and chemical energy. So mechanical energy is associated with motion or position of an object. Thermal energy is the movement of heat. So we're talking about the flow of heat from warm to cooler objects. And then chemical energy is the breaking and reforming of chemical bonds. Now, conservation of energy states that energy is never created or destroyed. It's always just transformed. So we can never create energy, or we don't ever destroy energy. It's just transferred into something else. All right. So in a chemical reaction, we might create compounds that have less energy stored in their bonds, or we might create compounds that have more energy stored in their bonds. And that energy can't come from nowhere. It always will come from something else, or it might go off as something else, such as heat. So if a chemical reaction, if heat is given off, we call that an exothermic reaction. So when heat's given off, we would have energy in the product side. So it's always going to be reactants are going to break down and form products. This will happen when we have energy stored in the bonds of the reactants is greater than that of the energy stored in the bonds of the products. So the products have a lower energy in their bonds than the reactants do. Conservation of energy states that energy is never created nor destroyed. It's always just transformed from one form into another. So we never can come up with energy all on its own, and we also never get rid of energy altogether. It's always just transformed from one type to another. In a chemical reaction, the energy is in the form of, if the energy in the form of heat is given off, then the energy is exothermic. So if we have this energy stored in chemical bonds and we have our reactants that have a certain amount of energy stored in their bonds, and they rearrange and form products with lower amounts of energy in the bonds, then that energy has to go somewhere. So often it'll be released as heat. We call this an exothermic reaction. So when we have an exothermic reaction, energy is always going to be on the product side of the chemical equation. All right, so basically what we have is we have our potential energy, which is the energy stored in chemical bonds. And if you can look at this, we see our reactants have more energy stored in their bonds than the products. Now, it doesn't mean that the reaction is just going to go without having to add any energy. But the added energy, it gets to that activated complex, is what's needed to get the reaction moving and get it started. And then the products, if you'll look at this graph, have a much lower energy than the reactants. That energy doesn't disappear, it's released as heat. Some examples of exothermic reactions are wood burning, fireworks exploding. Anything where this heat is being released out of nowhere is going to be an exothermic reaction. And if you guys remember doing the mini lab the other day, you guys saw that one of those sides got very warm, and that would be exothermic reaction. The heat is being released. Now, not all reactions release heat. Some of them will actually absorb heat. So they're going to take heat from the surroundings and use that to make products that have more potential energy than the reactants. If energy is absorbed, then it's considered to be an exothermic reaction. So if you have an exothermic reaction, if afterwards it feels cold, the beaker feels cold, or you can feel cool, then most likely it's an endothermic reaction because it's absorbing energy. When this occurs, you're going to have energy or heat on the reactant side because it's going to be going into the reaction, so it's going to feel cooler. It's absorbing energy from the surroundings. So we have here an endothermic reaction. You can see the products has more potential energy than the reactants, so it had to absorb energy from somewhere. All right, so not all endothermic changes feel cold at the end. Sometimes a substance can get warmer too when we're dealing with a phase change. So phase changes where you add heat to it to form either melting or boiling, they actually feel warmer. If you melt ice, it starts to feel warmer, but that is an endothermic change. So ice and heat is water, water and heat is steam. So don't get confused. Just because it feels colder doesn't necessarily mean it's endothermic. Sometimes endothermic reactions feel warmer, so you have to look how the heat is getting applied. And if you think about it, to change ice to water, you must add heat to that. And to change water into steam, you must add heat. The same goes with an exothermic change. The phase changes in the opposite direction, such as condensing and freezing, are actually exothermic reactions. So if you think about it, we have steam and it's condensing. We're cooling it off. We're releasing that heat. That heat has to go somewhere. The kinetic energy, they're moving more slowly, the molecules, so that energy then is released.